Welcome to this explainer. Today, we're going to deconstruct something that is just absolutely fascinating. The incredible, almost gravity-defying ways that modern buildings are engineered to survive unimaginable forces. You know, when you look at a towering skyscraper or a sprawling urban center, you probably think you're looking at a completely static object, right? Well, actually, scratch that. Today, we're going to completely flip how you view the built environment. We are diving into the architecture of resilience, and we'll unpack how human ingenuity is designing structures that don't just stand there taking a beating, but actively fight for their own survival.
But first, we really have to start right here. What actually happens when the earth beneath us just gives way? Imagine thousands of tons of concrete and steel suddenly subjected to the violent, chaotic kinetic energy of a massive earthquake, or maybe the relentless, crushing surge of a historic climate shift. I mean, the sheer, terrifying power of these natural shocks can literally turn a city block into dust in seconds. It's the ultimate test of human engineering. So how do we build against an enemy that can literally move the ground we're standing on?
To answer that, we're going to construct our understanding piece by piece. Here is our blueprint for today. First, the forces against us. Second, defining true structural resilience. Then, engineering for the impossible. Fourth, designing with nature. And finally, future-proofing our cities. Let's get right into it.
Okay, Section 1, the forces against us, nature's ultimate test. To really appreciate survival architecture, we have to treat nature as the ultimate antagonist, relentlessly pushing the limits of what we can build. Look, our modern safety standards are quite literally written in the rubble of past failures. Back in the 1980s, we saw some catastrophic rigid failures during major quakes. We used to build structures to be incredibly stiff, and, well, we learned the hard way that stiff buildings crack like dry twigs. That direct failure led to the 1990s, where we saw massive seismic building code overhauls all over the world. But nature kind of shifted tactics, right? As we moved into the 2000s, devastating superstorms really exposed our vulnerability to water, which prompted widespread flood adaptations. And now, today, in the 2020s, we aren't just reacting to single events anymore. We're implementing comprehensive climate-resilient mandates. Every single catastrophe has paved the way for a crucial engineering breakthrough.
Moving on to Section 2, defining true structural resilience, dynamic adaptability. This is where we really need a major paradigm shift in how we think.
So, what is architectural resilience? It's defined as the capacity of a structure to not only withstand environmental shocks, but to bend, adapt, and rapidly recover its core functions. Unpacking this is absolutely crucial. Because true resilience isn't just about stubborn, unyielding strength, you know? It's not about building a solid block of concrete that just sits there taking a punch. It's actually all about flexibility. It's about a building's ability to take that punch, roll with it, and immediately bounce back to a usable state.
Think about it like a giant anatomical puzzle. The old way relied heavily on rigidity, brute force resistance, that frankly acts like brittle, aging bones. If you apply sudden, extreme force to them, they just snap. The resilient way, though, that relies on flexibility. It's a highly flexible skeleton with strong ligaments and shock-absorbing joints. When the pressure hits, the structure contorts, safely distributing that energy rather than stubbornly resisting it until failure. It is essentially engineering martial arts, using the enemy's energy against it.
So how do we pull that off? That brings us to Section 3, engineering for the impossible, the physical mechanics. Let's look at how we actually build that flexible skeleton.
Let's walk through this process chronologically, because the physical mechanics here are truly awe-inspiring. When a shockwave hits a city, here is exactly what happens in a resilient structure. Step 1. Base isolation systems activate. Imagine placing a massive skyscraper on giant, high-tech roller skates or thick rubber bearings. The ground beneath moves violently, but the building just glides above it, completely separated from the worst of the shaking. Step 2. For any energy that does happen to travel up into the building, mass dampers absorb it. These are often massive, multi-ton pendulums suspended near the very top of skyscrapers. As the building sways one way, the pendulum swings the opposite way, acting as a giant counterweight to cancel out the momentum. And finally, Step 3, the core structural frame safely bends. Specialized joints and elastic steel frameworks allow the building to literally sway several feet in the air, harmlessly dissipating whatever kinetic energy is left. It's this beautifully choreographed dance of physics.
Now, you might be thinking, that sounds expensive. And you'd be right. It costs millions of dollars in premium upfront to install these base isolators and mass dampers. But to put that into perspective, look at what is averted. Hundreds of millions, sometimes billions of dollars in structural ruin entirely avoided. And more importantly, it ensures the building doesn't collapse, saving countless lives. When a hospital is engineered this way, it doesn't just survive the earthquake, it remains fully operational to treat the injured the very next minute. That is the ultimate return on investment, for sure.
Which leads us to Section 4, Designing with Nature, Symbiotic Architecture. We're currently seeing a massive ecological shift where architecture is moving away from fighting against nature and instead learning to work symbiotically with it.
We call this biomimicry. It's borrowing design secrets directly from biology, and it is a real game changer. We are now using things like permeable pavements for flood absorption, allowing water to pass right through the city floor and into the earth. We're installing living facades, buildings covered in engineered vegetation that act as a breathing skin to regulate temperature and filter the air. We even have biomimetic self-healing concrete. Seriously, this is incredible. Engineers actually embed dormant bacteria inside the concrete. If a microfracture forms and water seeps in, those bacteria wake up, feed, and literally excrete limestone to heal the crack. The building basically has its own immune system. And we're also using passive cooling via wind flow, actively shaping buildings to naturally channel breezes, which massively reduces our reliance on artificial power grids.
To really understand why this matters, just compare traditional concrete to these natural systems when it comes to floodwater absorption. Traditional concrete has an incredibly low absorption rate. Water hits it, pools up, and causes catastrophic flash flooding. Permeable paving is a huge step up, offering medium absorption. But when we actually integrate urban wetlands directly into our city grids, the absorption rate absolutely skyrockets. Designing these sponge cities massively outperforms the traditional stubborn, hard barrier infrastructure of the past. Turns out nature is just simply better at handling its own excess.
And finally, Section 5, Future-Proofing Our Cities, Macro-Level Adaptation. We've looked at individual buildings and specific materials, so now let's scale the whole concept up to the macro level.
There's this fantastic quote from our source material that I think summarizes this ultimate evolution perfectly. It says, "The ultimate architecture doesn't just bounce back from disaster, it bounces forward, adapting to a new reality." Think about that. This is the big shift from reactive repair to proactive adaptation. We aren't just trying to rebuild the exact same city after a storm wipes it out. We are designing cities that learn from the storm, evolve, and become fundamentally stronger and better suited for the climate of tomorrow.
So what does this all mean for us? Well, it leaves us with this final, incredibly vital question to ponder. Is your community built to resist the past or adapt to the future? The next time you walk down your street, I want you to really look at the concrete, look at the buildings around you, look at where the water flows. Are you living in a rigid system just waiting to be overwhelmed, or a flexible, resilient organism ready to bounce forward? It's a completely new way of seeing the world around us. Thank you so much for joining me on this explainer, and keep questioning the structures around you.